Hey everybody, I wanted to make us a video on our Chapter 5 notes. So hopefully everyone has been doing well this semester, and I know we're still trying to sort things out, but I'm hoping that this video and the slides can help answer a lot of the questions that I've been trying to field from you guys. And so the purpose of this chapter is really that we're finally moving into what I would call the more mathematical definition of what a group is. So remember, last semester we focused on a very intuitive definition that described groups in terms of actions, and I chose to use this definition because it allows us to get a better working understanding of what a group is in terms of actually visualizing it and manipulating it. However, that definition doesn't prove so useful if we wanted to prove theorems along the lines of, for instance, this set with this set of actions is a group. So basically, it's very difficult to prove things using the definition that we had before. So our hope or our intentions now is to try and build a much more rigorous definition that will indeed still be equivalent to the old definition. So basically our prior definition was using the rules 2.5 through 2.8 that we had from last semester, which stated that we would have a predefined list of actions. Each action would be reversible, each action would be deterministic, and any sequence of actions would be itself again an action. So this is a very useful definition, but we're going to try to improve upon it. And so we're going to introduce the more standard definition now, and we're also going to introduce the notion of multiplication tables. And multiplication tables can be thought of as being another way of representing groups visually, much in the same way that we can represent them using Cayley diagrams. However, multiplication tables can often provide more information than the standard Cayley diagram can itself. So when we draw Cayley diagrams from last semester, we typically allow the generators of the group to be the arrows. Now remember, there is a notion of ambiguity with generators because it is the case that the generators of a group are not unique. We typically strive to come up with the smallest set of generators. However, that is not in any way strict requirement. But once we have our list of generators, typically we try and have each generator be represented by a different colored arrow. Also remember that we can have unidirectional and bidirectional arrows. Any line that doesn't have an arrowhead is meant to be bidirectional, meaning you can move in both directions along that path. However, if there is an arrow, it implies a one-way direction of movement. And of course, what we know is because of Rule 2.8, what we get is that by using the generators to draw our Cayley diagram, we're actually going to recover all possible actions in the group due to the fact that compositions of actions are again actions, and since we can do this any number of times, we will be able to get every possible action as long as we actually have a complete set of generators. So what I mean here is, of course, if you just choose one action, it's possible that you'll miss something. Much in the same way, if you're only allowed to walk left and right, you can't get where you're wanting to go. But if you're allowed to walk left and right and forward and backwards, then you can actually get to the entirety of, let's say, R2 space. And so what we're going to try and do is clarify some things with Cayley diagrams and improve upon it so that we can move towards multiplication tables. So when we've been drawing Cayley diagrams, we've been doing one of two things. We will typically label each node as a configuration. So for instance, as a particular orientation of a rectangle or a square or a triangle, or even as a particular orientation of the Rubik's Cube. So then from that, we are able to draw several arrows leaving that, which are all the possible manipulations we can perform on that configuration. And these arrows will lead us to each of the possible outcomes of an additional manipulation. So it very much behaves like a roadmap where you're really just saying, let me diagram what can happen every time I take a single, most basic step. And then we also consider Cayley diagrams where we just leave the nodes unlabeled, where we're applying some level of abstraction. So last semester this corresponded to basically, we drew the Cayley diagram for the rectangle group, we drew the Cayley diagram for the light switch group, and then we said if we ignore the configurations at each of these nodes and just make them nodes, what we saw was the fact that these Cayley diagrams were exactly the same. So there is a notion of abstraction here that allows us to really study Cayley diagrams in a much higher level. So to clarify, let's go back to an example that we've considered, which is the rectangle group. So what I mean by the rectangle group is, of course, this groups of symmetries of a rectangle. Or for us, what this really means is all of the possible actions or manipulations that we can perform on a rectangle that preserves its original configuration. So what I mean here is if I draw my rectangle in the following way, anything that's allowed is something that results in a rectangle with the long sides being vertical and the short sides being horizontal. And the idea then is there are some very basic things that we can do. For instance, we can use a horizontal flip and a vertical flip as generators. And so what I mean by horizontal flip is, of course, flipping across the horizon. So meaning if I think of the symmetric axis through the middle, a horizontal flip would just be switching 1 and 2 and 4 and 3. A vertical flip would be something along the lines of switching 1 and 4 and 2 and 3. So this is what the blue and the red lines represent, respectively. And then what we asked ourselves is, using these, what other actions start to emerge? And of course there ends up being a third action, which isn't naturally or immediately obvious, which is equivalent to doing something like a 180-degree rotation. So we have the do nothing action, which is the original configuration or the identity. We have the horizontal flip, we have the vertical flip, and then when we compose them in either order, we get a novel action, which we can think of as being a 180-degree rotation. And then what you can convince yourself of is if you continue performing these actions over and over again, you will not get anything new. In fact, the only way to get anything new is to break the configuration or the geometry of the problem, which is the fact that the rectangle has to live in this kind of space. So, and so then the idea is, as we follow the sequences of arrows, we're able to see the result of applying generators and over and over again. And so what I mean is, for instance, you can just trace along. So you can ask yourself, what happens if I do a horizontal flip, horizontal flip, horizontal flip, vertical flip, vertical flip, vertical flip, horizontal, vertical, horizontal, vertical. And of course I could go ad nauseum here, but the idea is you see that you can very easily follow this map and determine what the output is. So I can provide you with, for instance, algebraic expressions to evaluate, which are very simple to do in this Cayley diagram. And all this is saying here is we have a way of arriving at a 180-degree rotation, and we ask ourselves, are there any other paths? And of course the answer is yes. In fact, there's an infinite number of paths that would end up being equivalent to 180-degree rotations. And so then the idea is we have lots of non-uniqueness here, but we really have some very important, let's say, basic representative elements here that we would want to consider. And the way that I like to think of this is as follows. We've talked about the integers modulo n. So think of the integers modulo 3, which is the set 0, 1, 2. And naively this is thought of as if I take any integer in the world and I divide it by 3, I determine its remainder, and I place it in a bucket labeled either 0, 1, or 2, depending on its remainder. So for instance, if I take the number 5, I divide it by 3, I get remainder 2. Similarly, if I, for instance, take the number 2 and divide it by 3, I also get 2. So they both go in the same bucket, even though they are very different numbers. And so what I'm trying to emphasize here is there are lots of things that are equivalent to the action, a horizontal flip. However, from, let's say, a group theory standpoint, I don't necessarily care about those differences. I'm only going to care about landing on one of these particular landmarks. Okay? So it's kind of like the integers modulo n, or for instance, you went to your local track and you show up and there's a lot of people on the track. And you can't tell how far anyone has went. All you can tell is where they are. So for instance, you've parked and you're walking up to the track and you see someone right here in one of the corners. You don't know whether they are just starting or whether they've run 20 miles. All you know is this is their position. And in some sense, that's all you care about, because since you're going to be entering the track to start your workout, typically you can think that you want to just avoid the places where people are, so you don't really care if this person's been running for a long time. All you want to do is somehow enter in a semi-empty space. Now, the entering of the track has nothing to do with group theory. It's just to help you understand that what we're seeing here are really landmarks or representatives, not necessarily all of the possible ways in which we can do something, just all of the unique orientations from those actions. All right? And so if we go back to that previous diagram here, and we basically take these rectangles and squish them into dots, saying I didn't really care that it was a rectangle, I simply cared about the structure of all my possibilities, then we end up with this abstract Cayley diagram, which last semester we called the V4 group, all right? Or the Klein group, or lots of other names for it. But for you, really all you need to understand is this is a very simple Cayley diagram that lots of things have had as their Cayley diagrams. Now, even though this is nicer to look at in the sense that there's not a lot of cluttering, we have definitely lost some information. And so what we want to do is somehow strike a balance between this very abstract representation and this very tedious representation here. And I'll admit, in this scenario, none of the representations are terribly difficult or easy to draw. I'm simply choosing something simple to represent. What you probably have realized by doing the homework is that Cayley diagrams can become very tedious to draw in this scenario, but the very tedious ones can become overly simplified in this scenario, and we almost have no usable information. And so this is what motivates our desire to strike a middle ground, which will be the multiplication tables. So, in order to really, let's say, draw these multiplication tables, we need to make sure that our Cayley diagrams are giving us everything that we need. And so in particular, we want to make sure that it's focusing on the group's actions rather than its orientations. All right? So we want to choose some node as our initial reference point and call it E, our identity, or our do nothing. So the idea here is it doesn't really matter. You simply need to choose a base point. All right? So in the previous slides, our base point was thought of as being this numbering. There was nothing wrong with starting with this, this, or this. All that would happen is it would simply rotate where these colors emerge, but it wouldn't necessarily change the structure. I hope that makes sense. So you simply need to make an arbitrary choice. Let's say as humans we typically have standard choices that somehow follow the lexicographical ordering of something, meaning we typically like alphabetical or numerical orders, but you could choose anything at a whim. So you simply need to choose your reference point, and then you need to relabel each of the remaining nodes based on the paths that lead from the node E. All right? So what I mean is, rather than thinking of this node here as a configuration, I would simply think of this node here as H, meaning a horizontal flip, because it is the outcome of that action. I don't necessarily care about what the orientation looks like, because I could reverse engineer that. I simply want to say that this blue line is a horizontal flip, so I'm now going to call this node the result of performing a horizontal flip. Similarly, this node would be labeled V for vertical flip, and this node here we would either label HV or VH, because we've performed both of them, or more than likely we would label it R, which would be our notation for a rotation. So what I'm trying to emphasize here is that we're not doing really anything different other than rather than trying to draw these giant pictures, we're simply going to just give it the shorthand notation that we're giving to each of our actions. All right. And then, basically, after we leave the identity, we will continue to label the arrows using the generators with colors, but then, of course, give newer and newer names. So the idea here is we're only still using red and blue lines, even though here this is a new action, it is from a sequence of the same basic actions. All right? So this is going to be the I've called it a definition. Really, it's an algorithm that allows you to make sure that your Cayley diagram is now in the correct form so that you can create multiplication tables. All right? And so our convention will typically be to label the nodes with sequences of generators so that reading the sequence from left to right indicates appropriate paths. Now what this is really saying is emanating from the identity, all of your immediate connections should be generators. After that, there will be the non-generator actions that are generated through continuous compositions. All right? And so, just as I had said, we now have our diagram of actions. And this still is the same Cayley diagram. It still has the same information. But now what we have is we can see I don't have to draw the giant rectangles, but now I have a lot more information. In fact, one can construct a bijection between these much simpler labels and the actual original orientation. So mathematically, we're actually still preserving all of our information. All right? And so another thing to notice is I could either write VH or HV here because the order didn't matter for this particular group. However, hopefully what you've realized by now is that is not always the case. You can always think of this as the socks, shoes property. Sometimes it doesn't matter the order in which I do things. Right? You can put your right leg in your pants first or your left leg in your pants first. Either way, your pants end up coming on. However, it does matter whether you put your shoes on first or your socks on first. So there are particular operations in which order matters, and so we have to be very careful about that. In this situation, it didn't matter, so we have a level of arbitrage in the sense that we can arbitrarily choose what we want. All right. So basically, what we want to do now is just make sure we've understood this process so that we can continue doing it for other ones. And so the first thing is we can start asking ourselves, when we have this equality in the sense of the commutativity of actions, is there a nice way of representing it? And the answer is yes, of course, through a mathematical expression that says HV equals VH. This is simply saying that the order doesn't matter. All right. And another thing to note, and this is something you guys have been asking on the homework, if you forget which arrow corresponds to which generator, simply trace it back to the identity. Right? From the identity, I can see blue must be H and red must be V. All right? Because the identity serves as our base point. All right? And then, once we have this, this actually serves as a sort of calculator. And this is what I was saying before. So, for instance, if I wanted to know what H, H, V, V, H was, then basically what I would do is this. I would do an H, then an H, and then a V, and then a V, and then an H. And I see that the output is equivalent to just an H. So I now have really a calculator of sorts that allows me to compute lots of different operations. And this is what's going to be very helpful in order to draw our multiplication tables. So this is a different one from what I've just said, but hopefully you've kind of gotten the gist of it. We can go H, 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 V, H, V, V, V. So let's start over again since I actually accidentally clicked. H, 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 V, H, V, V, H, V. And it's equivalent to H. And so we can condense this writing. By any time we have repetitions, we can use the standard power notation to represent that we're performing this operation multiple times. Now, the question you're probably asking is whether I can write this in this much shorter notation, because that's what we would do, for instance, if we were simplifying an algebraic expression when we're teaching, I'm always off with this, but let's say something like 4th grade algebra. And the answer is, in this case, yes, but that's only because we're able to perform these operations in any order we want. Remember, we talked about this, that VH equals HV, and that is why we can do this shorthand notation. However, this is not always true, so you must be very careful. I would suggest never really writing it shorter than you need to unless, let's say, explicitly asked or you're very sure. Because in general, these two representations would be very different depending on your group. All right? So now that we have the ability to actually perform operations, we can now start to create multiplication tables. And multiplication tables are really something that tell us everything that we need to know about combining all of our possible actions. So this is how it works, and it works a lot like the classical multiplication table you learned very early in elementary school when you learned your 12 by 12 how to multiply numbers. So since this group has 4 distinct actions, we're going to have a 4 by 4 multiplication table. And the goal is to describe how each action interacts with the others. And once you understand how this works pairwise, and the nice thing is, since this is a group, I can in no way create a 5th new action, right? Because of this closure property guaranteed by Rule 2.8, I can't somehow combine these guys and get something that's not here. Then these are the only pairwise actions I need to consider, because the output will once again B, something that's on the original group, and I can just compose these things over and over again. So this really tells me every possible way that I can do a computation in my group. So how do we go about it? Well, first of all, you simply list your elements on each side of the table, and then it works pretty simple. And you can see I've kind of color-coded so that it's very clear where things are being represented. But when you're filling this out, step one is the first row is just exactly whatever is right here, because anything composed with the identity leaves it unchanged. So however you've listed these, they go in the first row. Similarly, however you've listed these go in the first column. So immediately you can fill these parts out for free. All right? After that, that requires us to do some thinking. So for instance, you might say to yourself, look, the identities emerge on the diagonals here. That is pure coincidence. This is not something that always happens. Similarly, you might say to yourself, we have some symmetry across this diagonal. Once again, that is coincidence. That does not always happen. So how do we go about this? So let's leave this upper left little grid that we kind of understand, and let's start doing some simple computation. So let's see, what is V composed with V? Well, really what that's saying to do is to start at E, perform a vertical flip, and to perform it again. And since I end back up at E, the answer is E. And then we ask ourselves, for instance, what is a horizontal flip composed with a vertical flip? Well, I do horizontal and then vertical, and my answer is a rotation. Similarly, I ask myself, what is a rotation composed with a vertical flip? Now, the key here is you have to understand what the rotation means. The rotation means you have to do blue plus red or red plus blue. All right? So if we want to do a vertical flip, we do the vertical flip, and then we do a blue plus a red, and we get that it is a horizontal flip. All right? Similarly, if we go the other direction, I can ask myself, what happens if I do rotation and then vertical flip? Well, then the idea is you do the rotation, and then you do the vertical flip, and you get an H. Similarly, if you rotate the other way, you still get the same thing. And there's still, let's say, a level of choice here in terms of which one you want to say is your left element and which one is your right. I typically let this be the left and this be the right. However, it will be clear to me what you're doing based on how you write it. And we proceed to continue filling things in. H composed with H, so we do an H and an H again. We get E. Rotation with rotation, so there's a rotation, and there's a rotation, is E. And this is how we fill this out. Basically, this calculator allows us to fill out each of the individual squares here. And what we have now is this multiplication table, which tells us a whole lot more. All right, it tells us how every action interacts with every other action, so that I really have a more complete map of my group that is much more usable to us as humans, in the sense that I think we understand multiplication tables very well and can use them to do lots of nifty actual calculations. So, the first column and the first row repeat themselves for exactly the reason that we've talked about, that we're composing against the identity. Multiplication tables can reveal patterns, and these patterns I'm trying to make more clear with the colors of the cells. Now, you might say, what are these patterns? Well, for instance, the group is a billion, which means that every possible action is commutative, if and only if it's symmetric about the main diagonal, which is what we have here. There's a diagonal, and it's a mirror image across that diagonal. So, this is because of the fact that it's commutative. Moreover, in each row and each column, each group action occurs exactly once. So what you should see here is, if I fix the column, there's only one color of each. If I fix a row, there's only one color of each, meaning there's not two greens in one row. And this is something that's actually very important. This is a fundamental thing of a multiplication table, and it actually can be stated as a theorem. An element cannot appear twice in the same row or column of a multiplication table. And we can prove it. So suppose that in row I, so what I mean by row I is if we let one of these be I, for instance V, when I say row I mean that it's the element I in the group, and I'm fixing the row that is to the right of it. All right. So if I'm in row I, let's suppose that the element G appears in columns M and N. So once again, if I'm in row I, it would mean something like I have a color green here in column M, and a color green here in column N, which I don't have here, but this is just letting you understand the notation. Algebraically, this means that I composed with M from the right is equal to G, and I composed with n from the right is equal to g. That's what a multiplication table represents. Now, multiplying everything on the left by I inverse. Now, why can we do this? Well, our old rules tell us that every action is reversible, so there is some reversing action. I don't know what it is, but I'm going to represent it with this notation, I inverse. Hopefully that makes sense. This is the undo I. So, and the idea is I can't do it on the right because I don't know that I can switch the orders. So, I'm going to undo I, which of course is going to cancel I here and cancel I here. And this is just a fixed object. And what am I left with? M is equal to the same thing as N is, so M and N are equal. So, what does this tell me? I'm supposing that there are, let's say, I didn't say it explicitly, but there are two distinct columns M and N in which G appears. And I arrive at a contradiction that states that no, they cannot be distinct. Therefore, G cannot appear twice in the same row. I'm not going to prove it, but the proof for columns go exactly the same. I'll let you try and write it up. But loosely speaking, all that happens is you have to multiply on the opposite side in order to make this work. So, this is a very important thing. So this gives us two nice, let's say, computational features. One is if I want to compute my table, I can check myself. Because if I violate this rule, the fact that each element can only occur once, if it's violated, then I know I've made a mistake. Similarly, if I give you a multiplication table and this rule is violated, then that's all you need to state in order to say that it's not a group. So this is enough to say that the entire set is not a group. So let's do a more exotic multiplication table here. Now, I'm still answering lots of emails, and some of you guys are asking questions along the lines of, can I get more information about these groups? What do they mean? What do they represent? And these are great questions. But let's say at the moment, that's not my focus or concern here. As we get into later and later chapters, I'm going to introduce particular features of groups that are important. And as we see these features, we're going to talk about groups in more and more details. So, as unsatisfactory as this may be, what I'm really looking for you to do at the moment is really just do rote computations to get the hang of it. But if you'll recall from last semester, this group here is or this Cayley diagram here is equivalent to the symmetries of an equilateral triangle. So let's say, ignoring what all this means, because we may have forgotten, this is basically saying assume you have a triangle, so watch the mouse. So an equilateral triangle, 3 sides, same length, and you label 1, 2, 3. What are all the possible ways that you can manipulate your triangle? Well, you have rotations. What do I mean? You have 120-degree rotations. So you send the 1 to the 2 to the 3, the 3 to the 1, and you can do each of those 3 times. So rotate, rotate, rotate. Or let's do, sorry, I have it set up on the inside. Rotate, rotate, rotate. Similarly, you have flips. So what do I mean? If you have your triangle with the point on the top, then you can flip about the vertical line that passes through that top point, which in this case would correspond to flipping 2 and 3. So what we have are the blue lines represent flips, the red lines represent rotations, and we can compose those together in lots of different ways. So I probably should have put this in the slides, but let's say you have the ability to go back into your notes and see where we originally drew this diagram to correspond to the equilateral triangle. Another way you can think of this is the permutations of the numbers 1, 2, and 3 as a set. Now, but for us, what we're really looking to do is to compute. So what do we have here? I have 1, 2, 3, 4, 5, 6 distinct actions, which I will list here and here. Similarly, I will then have the first row is just a repeat of the outer row, and the first column is just a repeat of the outer column. And then after this, we need to do some computations. So, for instance, what is R composed with R? Well, I start at E. It's clear that the red arrow is R from my Cayley diagram, so I do red arrow and then red arrow, which is R squared. Great. Similarly, I can ask myself, what is R squared composed with R? Well, that's R squared with another red arrow, so that's E. Then I can ask myself, what is a flip composed with R? So what do? We perform a flip, we compose with R, and we get that it's equivalent to R squared F. So the same thing as doing 2 rotations followed by a flip. Right? So the idea is if we do a flip first and then a rotation, it's the same thing as doing 2 rotations and then a flip. What if I do a rotation and a flip followed by a rotation? So what do? A rotation and then a flip followed by a rotation takes me to flip. Similarly, 2 rotations and a flip followed by a rotation. So we have 2 rotations and a flip followed by a rotation is equivalent to just a single rotation and then a flip. And I won't keep doing each individual one, but hopefully what you're catching on to is we now have a very simple way of calculating if we have the Cayley diagram. And what this tells me now is, let's say loosely the same information, but sometimes in a much more useful way. Once I have this table, I can start looking for patterns and seeing where repeating terms start to happen and if there's any symmetries. And let's say this table doesn't look terribly symmetric or nice, but as we go further and further into our studies, we'll see that there are things that we can glean from this table that are a little bit beyond what we can deduce now. However, my goal right now is to make sure that you understand how to generate these tables. All right. Now, this is another group that you have asked several questions about. And let's say in my slide, I think I maybe have this backwards from how I actually should have put this, but let's say the labelings are arbitrary. Basically, this group is called the quaternion group. It shows up a lot in theoretical physics. Basically, what you can imagine is if you think of the real numbers as being just a single number in the real numbers, then what you can think of as the imaginary numbers, you have a real part plus an imaginary part, which is two-dimensional. It's like x's and y's. So what you can think of is you started down here in the single line, and then you added a dimension to it that goes upwards. Right? So now you have this entire flat piece of paper. And then what you can do is you can basically add another imaginary direction, so to speak. So you can come out of the board, and then additionally you can add another imaginary direction, which would be what? Coming out of the board gives you a box, and let's say the box is your world. And then you can add another direction by saying the box can move in time. So you have box 1 and it goes over to box 2. Now, the physics of this is not terribly important. What I want you to take from this, and the purpose of this was not to confuse you with the fact that there's another group that you need to understand. The point of this was to say, here is a Cayley diagram. And really you don't care what it's coming from. This is a group, it's a Cayley diagram, and it's labeled. Now the goal is to construct the multiplication table. And let's say these are two equivalent representations. They may look confusing, but the idea is through untangling, this is equivalent to this. Now, here's kind of the idea that you need to take from this. To draw your Cayley diagram, you need 8 elements. 1, j, k, let's say 1, I, j, k, negative 1, negative I, negative j, negative k. So you need 8 columns and 8 rows, and then you need to compose them in all the possible ways in order to get all of your outputs. All right? And the rest is just a description telling you that j and k act like the imaginary numbers because they square to negative 1, and multiplication of their elements work like cross products of unit vectors that you saw in Calculus 3. So in Calculus 3, you learned, for instance, if you think of these as the I, j, k vectors in R3 from Calculus 3, and you think of this product. So what I mean is the juxtaposition of them beside one another as the cross product. Then these things look similar. So they're not the same IJK from Calculus 3. And on some very abstract level, there is some equivalence here. But let's say at the low level that we're living in right now, it's almost coincidence that they look the same. And I'm simply telling you that these are just formulas that you can use to better understand the generation. So I didn't fill out the multiplication table for this because I wanted you to do it as a homework assignment, but what I wanted to do here is to describe to you that don't worry at the moment, and I'll try and answer each individual question as quickly as I can, but at the moment, don't worry about where this group is coming from because, in all honesty, it's coming from some abstract physics that would take some time for us to delve into. All you simply need to understand is, I have drawn a Cayley diagram. Can you represent the multiplication table for it? And if so, later on, we'll try and provide some more satisfying descriptions of what this group actually is. All right. So, with this in mind, we can now move towards the standard definition of a group. So we need to start introducing some notation that will help us understand that. So before we've been calling all the members of a group the actions. However, to move towards the standard element, we need to take more of a set theoretical understanding of it, and we're going to call members of a group elements, which of course now makes a group a set of elements that satisfy some additional properties. And just as we do in basic set theory, we'll write things like this. The group element H is an element of the group V4. And this epsilon here is simply the inclusion operator that you've seen in set theory, meaning that if we think of this V4 as a box, H is in that box. All right? Now, then we need to understand binary operations. And in last semester, one of the very first things I had you do was actually explore operations, because I thought they were simple enough to give us that traction that we needed to feel good about understanding abstract math. But we're coming back. And intuitively, operations are nothing other than a method for combining objects. You can think of operations as just ways of taking pieces and gluing them together, or combining Lego pieces, really. We represent these in lots of different ways. Addition, subtraction, multiplication, division, these are all operations, because I can't add just a single number, right? I have to have two numbers being combined together, hence we call it binary in this situation. All right? So we will use the asterisk or star to represent an abstract binary operation. This might be plus, minus, multiplication, division, a million other operations, but the idea is it is a binary operation on a set. So we have a box of elements in S. Star is a way of taking two of them and combining them together. And it is a binary operation. Then, if I take two elements and put them together, then it's not anything new. So I want to make sure this is very clear. This line looks very funny, but what it's saying is you have a binary operation on a set. If you take two things out of the set and you glue them together, it's not anything new. That was already something in the set, which should sound a lot like what we have for groups, right? We have that if we combine actions, we don't get anything new. So this is simply saying that if we combine elements, we don't get anything new. And the idea then is for this binary operation, if this is true, the set S is closed. So closure is another mathematical term that you've probably heard. But basically what we have here are two new things. Binary operations, which are methods that allow us to combine two objects in a set. And the idea is if this combination doesn't result in something new, then we have closure. All right, so these are, let's say, not competing with one another. These are things that actually have to both simultaneously be true for our definition of a binary operation. So we have an operation and we call it binary if it is closed. And of course, binary. So the combination of group elements is a binary operation, and we say that it is a binary operation on the group because it's defined on that group. All right. And so from Rule 2.8, which says that any sequence of actions is again an action, we have that the binary operation, which is combining actions or composing actions on a group, is a closed binary action. All right. So we have that the group is closed. All right. And multiplication tables are nice because they fully describe the group's binary action. So there is no there's nothing left to determine because we've shown every possible way of combining two pieces. All right. So, and the other thing that really important to know is just any multiplication table with symbols is not going to be equal to the multiplication table for a group. And so basically this is something we've already started to discuss in terms of there needs to be one element in each row and each column and so on. But I'm just wanting to emphasize once again that just because you have something that looks multiplication table-ish doesn't mean it is a multiplication table. Hopefully you remember what it means for operations to be associative, and basically the notion of associativity is that parentheses are permitted in any order but required nowhere. So associativity is a way of saying that if I wanted to perform my operation on a sequence of objects, more than two of them, then the order in which I perform it is not important. So for instance, if you add a sequence of 12 numbers, it doesn't matter whether you group them into two groups of 6, 3 groups of 4, and so on, the result will be the same. However, addition and multiplication is associative. However, subtraction is not. And this is something we saw last semester. The order in which we subtract. So here, for instance, the parentheses dictates that this becomes a negative 2. 3 minus negative 2 becomes positive 5. Whereas here, this becomes a 1, and this whole thing becomes a negative 3. Obviously, those are not the same. So even though subtraction is a binary operation on the set of integers, right, is closed, there's only two objects on which it acts at a time, it is not associative because the order in which I perform the action is very much important. All right. So this is just to remind us of the definition of associativity. And similarly, you have a homework problem about exponentiation. And so the idea in there is somehow we're meaning raise something to a power and then raise that whole thing to another power. Of course, the order there will matter once again. So then the question becomes, what about combining actions in a group? Is that associative? Yes, it is. Now, this is something we won't prove, and I'll give you an example. What you should take from this is when you have groups, a key feature of a group is that the action will always, or the combining of actions will be associative, and this is something that we'll talk about with the actual rigorous definition. So go back to D3, the symmetries of the triangle, and then we ask ourselves whether I can just perform these in any order or whether these different orders matter. All right? And the idea is the actions are the same. Now, I won't go back, but what you should convince yourself of is if I follow my Cayley diagram doing rotation, flip, then rotation, or doing rotation and flip, then rotation, or rotation and then flip rotation, right? The idea is this is a separate, what you can think of as why this is subtle is these are 3 distinct group actions. These are 2 distinct group actions and 2 distinct group actions. So even though we don't necessarily have commutativity for all actions, we have associativity. So this is very important. So it just means in the end we can simply work left to right. Right? Now I hope this isn't confusing. If you have questions about this, of course, reach out to me. And so the moral of this is we just don't need parentheses when we're working in groups, although sometimes we may use them if we're wanting to emphasize a particular chunk or sequence. All right. Now, the next piece are inverses, and I think this is one that can cause a little bit of issue. All right. So, Rule 2.6 requires every action to be reversible, which is another way of saying that if you have an action, there is an opposite reaction. Opposite action, and we will denote this opposite action as the inverse. All right. Now, we will use the notation g raised to the negative 1, and what I want to first say is this does not mean 1 divided by g. Okay? So, the inverse simply means the reversal, and what that means depends heavily on the action. So, if my action was addition, this would be adding the negative. If I was multiplying, this would be multiplying by the inverse or dividing. If this were matrix multiplication, then this is the matrix inverse, which of course is not dividing by the matrix by any means. If I was talking about exponentiation, then I would be talking about undoing that exponentiation, right? Somehow raising it to the raising it to the 1 over the original power, right? There's lots of different ways that we can talk about the inverse, and the idea is it's all heavily dependent on how the binary operation is defined. Now, rigorously, we define it as follows. Something is inverse is if combining the actions, we get the do-nothing action. So if you skip down here to this equation, then G inverse simply means that if I have the action G and I apply G inverse, I get the identity. All right, and it doesn't matter the order in which I do it. Okay, so we have lots of ways of denoting the identity. E, 1, 0, N. These are all different things used in different scenarios. We will typically use either E, 1, or 0. But the key here is that the inverse is simply something that undoes an action, and the inverse has to commute, so it has to work on both sides. Okay. So to explore this a little more, let's go back to D3. So here is our calculation. Use the Cayley diagram to complete the statement. So what is R inverse? Now, unfortunately, there are lots of valid answers. But let's go back to the definition. If I have R inverse is just something that takes me back to E, but this guy, we want it to live inside of the group. Okay, so I can't just leave it this way. I need to write it as something that makes sense. So, if I have R, how do I get back to E using the Cayley diagram? Well, I can perform R and then R again. So R squared is R inverse. So basically if I rotate by 120 degrees, I can undo that always by performing a 240 degree rotation. That's not the only answer. What is another answer? Another answer would be if I perform R and then I perform a flip and then a rotation and then a flip. It tells me that flip, rotation, flip is also another representation of R inverse. Both of these are fine because they're in the group. Okay. So, and what we can convince ourselves of is a lot of these things end up being equivalent if we want them, if we want to think that way, but this is how we can compute them. So, what about H inverse? All right. So, the idea is, let's see. Oh, I probably actually realizing what I've done here. That should be an F. Sorry about that. So, I'll update the slides, but hopefully as you're listening to the video, you realize that this should be an F. So what is the reversal of a flip? Well, if I flip, I can undo a flip with a flip. Right? So flip is its own inverse. Then I can ask myself, what about a flip and then a rotation? So if I do a flip and then a rotation, this is equivalent to this guy right here. Right? And then I can undo it with a flip and a rotation. Right? And so what I'm trying to get at here is we can figure out what our inverses are by basically starting at the identity, performing the action of interest, and then simply finding a path that takes me back to the identity. And in some groups this can be pretty easy, and in some groups it can be more tedious. But the key here is this inverse notation is simply saying not that I'm dividing. It could mean it sometimes, but not always. The key here is it's saying that I should be undoing whatever action I have just performed. All right? And so now we can actually define our classical definition of a group. So, a group is a set with a binary operation where that binary operation is associative, and inside of that group there is an identity element, meaning some element that leaves every element unchanged with respect to my binary operation, and every element has an inverse with respect to that operation. So, let's think about what this is telling us. So this is our rigorous definition. This is something that we can prove theorems with. But let's think about what this is telling us. First of all, we have a set. So this set is just a box with a bunch of elements. And what we can remember is that elements have replaced the name for actions. So this is somehow our predefined list of actions. Okay? Now, we have a binary operation on the group. Now remember, the binary operation implied closure. All right, so now we have closure, and this means this associativity means that we can really do things in any order we want, and it will be okay. So 1 and 2 together really correspond to, let's say, Rule 2.8, which is that any combination of actions is once again an action. All right, so we have this closure in any order. We have the predefined list because of the fact that it's a group. Then we need, and also let's say underlying all of this, the fact that the binary operation is defined means that it is deterministic, the fact that we can give it a definition that makes sense. And then rules 3 and 4 tell us that things are reversible. Basically, to know that it's reversible, which is the fact that it has an inverse, I have to know what my base is, right? I need a reference, and that's what the identity serves as. So I can't know that I'm reversing something if I don't know how to get back to where I started. So 3 and 4 together really give us a notion of reversibility. So loosely, what I'm trying to say here is hopefully you can see how the 4 rules that we laid out in the earlier chapters can be seen as being loosely equivalent to what we've laid out here as our rigorous definition. So this is a definition that you should really spend some time dissecting and understanding because it's going to be very, very important as we move forward. Now, depending on the context, I might use lots of different symbols to denote our binary operation, but a lot of times I'll simply not write the operation. I'll just simply write 2 elements juxtaposed beside one another, and you should infer that there is some operation being performed. I will only use the plus symbol if the group is abelian, meaning the action is commutative. So of course this could mean integer multiplication, matrix multiplication, real number, or sorry, not multiplication, integer addition, matrix addition, real number addition, or it could be something more exotic, but the idea is if the order doesn't matter, I may use the plus symbol. The plus symbol is really used to imply that there is commutativity. However, if I'm just juxtaposing, it is not necessarily guaranteed that we have this commutativity. All right. Now, uniqueness of the identity and the inverses is not built into the definition of a group, but you can prove this property. All right. So so there is no uniqueness there, right? Nothing in this says that these things are unique, but you can prove it. And let's say, Now, before I move on, you might say, but remember, we were drawing all these paths before on D3, and there were not unique inverses. So, remember, though, we can think of it as being kind of like the following. If I'm thinking about the integers modulo 3, so 0, 1, and 2, then adding 3 or adding 6 or adding 9, they all end up with the same output, even though they're very different inputs. So what we have is, even though there's a bunch of different paths I can take, in the group setting, if we work and think about it, it's actually the case that they will all reduce to some unique fixed kind of reference. So, and so this is just to once again emphasize what we've been talking about. We have two competing definitions. One is very informal and one is very rigorous. Do they agree? Or at the very least, does our informal imply that something is a group with our more strict definition? Does that make sense? So we have the old definition. If it was a group by the old definition, does it imply that it's a group by the new definition? Hopefully my description before loosely convinces you that the answer to the first one is yes. Does the rigorous definition imply that it holds true to the informal definition? That one's a harder question to answer because of the fact that it's hard to prove things with such an informal statement. But hopefully you understand that the first one's yes, and we'll answer the second question in the next chapter. So, if the definitions didn't agree, we would be in a very bad situation. I have somehow created two competing theories, and that's very bad. But what we're going to have is, yes, they are in fact equivalent, and we will demonstrate this later. But regardless of whether they agree or disagree, we always have that the reverse of the do-nothing action is do-nothing. So this is something that's always true, and this is something that we can use to actually build upon answering these questions that we've just mentioned. All right? And so even though we haven't shown that these things agree, and in some sense we can't because of the level of informality that the first definition have, we now have two different paradigms of viewing groups. A group can be a collection of actions, and a group can be a set with a binary operation. Now, the second is the one that we're going to spend some time trying to do with the rest of the semester. The first is how we started the semester, and the idea is the first one gives us very good intuition. The second one lets us prove things. All right? Now, and just to give you an idea, we can prove things very simply. For instance, every element of a group has a unique inverse, and how we prove that. So let little g be some arbitrary element of a group G. Now, there's a lot being said by saying group capital G. This means that group capital G obeys definition 5.2. It's a set with a binary operation, and that operation is closed, and there's an identity, and there's inverses. So there's a lot of structure with just this word group. So by definition, it has at least one inverse. That's what the fourth property says in that definition 5.2. Now, suppose to the contrary that there are two inverses that I denote H and K. This means that GH equals HG equals E, means that H undoes G, and also that K undoes G. So, our contradiction will be demonstrated if we can show that H and K are the same. So, H, which is the same as H against E because E leaves things unchanged, but a fancy way of writing E is just GK because of this second property right here. But since my operation is associative, I can move the parentheses, and HG, by this definition, is just E, but the do-nothing action applied leaves K. And when we string these together, H is indeed equal to K, which implies that H was equal to K the whole time, which means that my supposition that I have two distinct inverses is false. So, inverses are unique. Similarly, you can show that identities are unique, but I'll let you guys ponder on that yourself. And so, as always, please email if you have questions. Of course, we've already pointed out that there was a typo with my discussion of the inverses of the elements inside of D3, so I'll fix that. Several of you guys have also pointed out typos in the notes, which I will be updating as well. But other than that, feel free to email me if you have questions. Let me know if you're struggling with the homework and if we need to move the due date that has been arbitrarily set as, I believe, February 3rd. And otherwise, just keep working and make sure that you guys are staying in touch with me and reaching out at least once a week. All right, thank you.